Hello, welcome back. In this segment, I wanted to review a section of this paper, Secure Multi-Party Computation. There is a section on RSA. This is called threshold cryptography. The core idea of this section is that how can we split the private RSA key that is used for decryption into two pieces and distribute the pieces into two different nodes. That's basically the idea. Okay, I will talk about it. First, I will quickly recall the syntax of RSA, the RSA functions. I'm going to use the notations that are used in this paper. It may be slightly different from what we have been using in the previous segments, but that's okay. First, I will show you very quickly the RSA function. Okay. So RSA has multiple steps. One is the key generation step. P and Q are two random primes. They are secret. We multiply them and compute the product. As you know, given n, it's difficult to find P and Q, as far as we know. That's the reason why RSA is using this construction. And we compute Euler's torsion function on n. We could also compute lambda function we talked about earlier. Okay, Carmichael function as well. Anyway, let's use pi of n. That's what the paper uses. Pi of n is p minus 1 times q minus 1. And then the key generation phase also generates two numbers e and d, such that e times d is congruent to 1 mod pi of n. Okay, for this to be true, e must be relatively prime to pi of n. If e is not relatively prime to pi of n, you have to throw away the p and q and regenerate it until you can find a d and e which satisfies this equation. Okay. Once you generate E and D, you can go ahead and destroy P, Q, pi of n, because if you leak any of those, the whole thing is going to be broken immediately. We talked about that as well earlier. So the public key is n comma E and the private key is D. And the public key is published to the world. So anyone who wants to send a message to you will use your n and E, and you will be using your D to decrypt their message. So the encryption function is a number from Zn to Zn, meaning a number from 0 through n minus 1 through 0 through n minus 1. Okay, so x is your message. In the past, we used m as a message, but in this article, they're using x. That's perfectly fine. X power e mod n will give you y. Y is the ciphertext. You send it to the recipient. The recipient will take your y and apply the secret private key d to recover x. We already proved how this construction works. So I'm going to assume you know how RSA works. I will dive into the threshold cryptography, where instead of storing the D at one place, we will split the D into two parts. We could split it in multiple parts, but for this article, the example is only to split it into two parts, D1 and D2, okay? And do the decryption in a distributed fashion. Okay, let's go ahead and do that. So here is the setup that I have been talking about, threshold RSA. A client can be a web browser, for example. It wants to send a secret X to the server. Of course, if you send X in plain text, anybody can sniff the channel and get it. So you, as a client, apply encryption function, RSA encryption. Take your message X, raise it to power E mod n. E and n are public parameters of the server. Server publishes E and n to the world. So anyone can use this as part of the communication. And they encrypt n and E. You can imagine server sends the N and E via digital certificate. At this point, you can imagine N and E are public, known to everybody. Okay, you will send the Y to the server. And then the server, instead of directly decrypting Y and obtain X, what it will do, it will send the Y to node 1 and the same Y to node 2. You see here, Y is sent to two nodes. Y itself is a ciphertext, so it's okay to send it in clear text, of course. Okay, but you can see here, the decryption function requires here D1 and D2. I have to define what D1 and D2 are now. So the server actually, before performing these operations, it will generate two random numbers, D1 and D2, such that D1 plus D2 is congruent to D mod pi of n. And you can imagine that server safely installed D1 here and D2 here. So D1 and D2 are private, okay, to be clear. It is hidden in node 1, hidden in node 2. You can imagine there's a secure channel where the server initializes D1, server initializes the D2, and then server will go ahead and destroy D1 and D2 on the server side, and D as well. So D1, D2, D, pi of n, all of them are destroyed. So anyone who hacks into the server alone will not be able to get the decryption key because it's stored in two different places. It's stored at node 1 and node 2. Of course, if there's a malware sitting inside the server at the time of this operation, then it will know D1 and D2. But that's something we can't solve by any means. Here, currently, we assume that the private key D is never stored explicitly in anywhere, right? D is destroyed after D1 and D2 are generated, and D1 and D2 have to be securely stored, of course. Otherwise, anyone who steals D1 alone will not be able to solve this easily, as far as we know. They have to steal both D1 and D2. That is the reason why I shown here D split into two parts, D1 and D2. Okay, and then the node 1 performs basic RSA decryption. Node 2 performs RSA decryption of Y, but uses D2. Of course, node 1 will use D1. And node 1 will reply to the server X1, basically the decryption of Y using D1 as the key. And node 2 will reply to the server after decrypting the Y using D2. So basically, the server gets back X1 and X2, and he multiplies. And why is this equal? I'm proving it here. So you take X1 and X2. Well, how is X1 computed? Y power D1 into D2. So we can add the exponents. I'm going to make an assumption here that Y is a group element, Z star N. In that case, computing Y power D1 plus D2 is same as computing Y power D1 plus D2 mod pi Fn. D1 plus D2 is nothing but D mod pi Fn. Therefore, we can replace this whole thing by D. That's why we get Y power D mod N. This is a regular RSA decryption, which we know is X. Okay. This proof assumes that the element X that you are the center sending is an element of Z star N, which is the highly likely probability. If X is not in Z star N, your RSA is already broken. We talked about that earlier. As a homework, if you wanted to convince yourself the same thing works, you can apply Chinese remainder theorem to prove that if your X is not a member of Z star N, this equation is still true. Okay, meaning X1 times X2 is congruent to X mod N is still true. All right, that's basically it. Essentially, you're splitting your D, the private key, into two parts, D1 and D2, and you're storing D1 and D2 in two different nodes. So somebody comes here and attack will not be able to decrypt because they don't know the key D2. And the same you can argue if somebody only attacks here, they can't decrypt because they don't know the other portion of the key. Okay, so the attacker has to compromise node 1 and node 2. Okay, this is in contrast to the past where we assumed that the server has the private key sitting here somewhere. That means only attacking the server key is enough. Okay, now you have to attack two places. That's basically the idea. One more thing, if you are familiar with RSA, the internals, I'm explaining in a way that's not exactly correct. There is some small difference in the way that it's used in practice. You will not directly encrypt your message X using this function. You will apply padding. Padding is introducing randomization to your X, usually. That's how you will use it. In that case, what you have to do is when node 1 computes X1, you have to disable padding check. Otherwise, there will be a padding error thrown by node 1 because you're using D1. Similarly, you have to disable padding check at node 2. Now you can get X1 and X2 and multiply it and you get X, right? You can double check whether everything's okay by re-encrypting the X using E and N and check whether it matches the Y. When you re-encrypt it, you have to disable padding because otherwise you can't get the same Y the client originally sent. Okay. After that, once you confirmed that the X is a good X, that node 1 or node 2 behaved in a bad way, then you can go ahead and remove the padding bytes. Okay, that's something you can do if you know about padding. That's the reason I'm explaining it very briefly and quickly. Anyway, so the main message is that it is possible to decrypt an incoming RSA encrypted message by splitting the private key into two different nodes.